Hello and welcome. My name is Charles Zona, and I would like to thank everyone for attending today's McCrone Group webinar. Our presenters today are Dr. Kent Rhodes and Dr. Craig Schwant of McCrone Associates. Kent and Craig are going to talk to us about the capabilities of McCrone Associates and employing what they call the particle approach. Kent is the Senior Vice President and Technical Director of McCrone Associates, and he also co-teaches our Scanning Electron Microscopy course. In addition to his management of technical services at McCrone Associates, he performs surface analysis using X-ray photoelectron spectroscopy, secondary ion mass spectrometry, and electron microprobe analysis. Craig is the Director of Industrial Services and a Senior Research Scientist with McCrone Associates. He is also a co-instructor for our basic and advanced scanning electron microscopy courses. Craig specializes in X-ray microanalysis of particles using energy and wavelength dispersive spectrometry methods with the scanning electron microscope and electron microprobe. Kent and Craig will field questions from the audience immediately following today's presentation. This webinar is being recorded and will be available on the McCrone Group website under the Webinars tab. And now I will hand the program over to Kent and Craig.
Thank you, Chuck, and thank you all for attending our webinar today. To begin with, let's just talk about particles. I think all of us have a pretty good idea of what we mean when we talk about particles. And those are just small, discrete pieces of a material. And they are surrounding us constantly. The air we breathe, the food we eat, all has particles in it. But I kind of like to divide them into different classes of materials. So a lot of materials are, by their very nature, particulate. The air, the dust in the air, the salt and sugar you use when you eat, those are fundamentally particulate in nature. Other materials go through a phase where they're particulate during the production of a final product. So for example, coffee is ground into particulate, extracted to form a final liquid material. And then the final type of particles that we deal with a lot here at McCrone Associates are contamination, which is basically foreign particulate matter, usually where you don't want it to be. And those turn out to be the most interesting projects because they're forensic in nature. You have to try and determine what the material is and perhaps where it originated from, with the ultimate goal, of course, being to reduce or eliminate that foreign particulate matter. So the slide you're seeing now are just a few examples of things like wear debris, a drug product, and then some foreign particulate matter, including a biological sample. Most of our presentation today, though, will be dealing more with inorganic contamination. So next slide, please.
As a tie-in to the previous webinar, which was on glass delamination in injectable drug products, this image is an example of some glass delamination flakes on a filter after it was filtered from the product. So in general, our clients are really interested in what is that foreign particle and how did it get there? Before we get to that question or those two questions, we want to consider some concentration really first. So if we use an example of, say, a particle in a volume of material, you might think you have a little piece of iron and it might be one speck in a large cubic meter of volume. And so you could say that was relatively 1 part per million. So if we had a cubic centimeter out of a cubic meter, that's effectively a 1 part per million concentration. So analyzing materials at trace levels requires one method. But when we look at particles, we often remove those particles from the matrix that they're in. So we actually start to look at the entire volume. So if we have an alloy that's made up of different components, say we're looking at this collection of M&Ms, and each color M&M represents a different alloy element in a steel. Well, iron actually is the major component. So if we focus our analysis just on the small volume at hand, then those constituent elements make up major percentages of our foreign particle. So concentration in that sense is really a relative term. If you're looking at a big volume, then you might be considering trace elements, but if you're looking at just the particle of interest, those elements are in major element proportions. Next slide.
Yeah, and just to convince you how daunting this analysis challenge can be, if you take the example of, say, 100 mLs of aqueous solution, put in 5 stainless steel particles, and this is a typical analysis request. We get contamination samples with very small numbers of particles. If you tried to do this by bulk analysis, as Craig just described, your analytical challenge here would be to measure this at the picogram per gram levels. This is a very challenging analysis for ICP, atomic absorption, or most bulk analysis techniques. But happily, we can take advantage of the fact that these particles are not homogeneously distributed through this material. If we can concentrate the particles for analysis, we have a much better chance of doing this forensic identification of the particulate matter.
So before we go on, just a moment, I mean, Kent, one picogram per gram, that's maybe a foreign way of looking at it for some people, but I think that's something like 1 part per trillion. Wow, that's pretty amazing. That is ultra trace detection.
Yeah, if you don't take advantage of the fact that these particles are heterogeneously distributed and in many cases can be concentrated, you are going to have a very difficult time measuring small amounts of particulate in large volumes of material. Because remember, there's also the sampling issue. You can't take just a milliliter aliquot of that and have any assurance that you'll have a representative sampling of the particulate matter.
That's right. So our next question is really, is the particle approach considered testing? And in that sense, it's not really testing. The particle approach is investigative or forensic analysis, as opposed to compendial or specified testing, where you're testing a product to a specification, either an ASTM standard, a USP standard, some standard where you know what the concentration of the elements should be, and you want to know in a testing situation, is your product compatible? Or also in the same time, if you are doing a regular testing method and then you perhaps do discover that there's an elevated concentration of a particular analyte, then that's when you would really need to look at investigative or forensic analysis. So we want to ask, well, what exactly is it? And that's our main question then, what we want to determine for the problem. And then we can ask versus how much is there? So most of the time we really want to know what it is rather than how much is there. Next. So this comes into play. We have quality elements involved really. With testing, again, you're really comparing the results against some specification, whether it's for standard or for your product specification. And you could do replicate analysis to improve your confidence in the results that you're measuring. This is in a different contrast really to investigational analysis, where we're going to perform periodic tests on our instrumentation. We'll also do periodic testing of our analysts to demonstrate that both the instrumentation and our analysts know how to give the right answer when testing known materials. But really, in an investigational analysis, we don't know what the answer is going to be beforehand. So we're doing a quality assurance task, whereas with testing, we're really looking at a quality control task. And so there's a big difference there. And these are things that you want to ask when you're considering what type of laboratory you need to address your particular analysis concerns. So the pros and cons with a bulk analysis testing method, it can alert you to the presence of contamination, but it's also relatively fast and cheap. But it really doesn't help you identify the source of your contamination, whereas the particle approach is able to explicitly identify contaminants using a wide variety of methods. It greatly assists in then identifying the source at the production plant. But the downside of it is that it can be a bit slow, and obviously it's a little bit more expensive because it may require multiple methods in order to come to a complete conclusion.
Okay, so with that background information about what we mean by the particle approach, let's talk about how we actually perform these kind of tests. We mentioned previously that really the first step and one of the most important is to concentrate the material or the particulate matter for further investigation. And there's a variety of methods we use here at McCrone Associates to do that. Probably one of the most common ones, and one that you might be familiar with, is filtration. So we do a lot of filtration. And one of the key points to realize here is that we really need to protect our samples from further contamination from the environment or from ourselves. And so we do most of our filtration in very controlled environments here at McCrone Associates, inside of clean rooms or laminar flow hoods, to reduce the background and make sure we don't further introduce additional contaminants that would just confuse us or provide information that's of no value on these particular samples. So if we go to the next slide, once we've concentrated these particles, we have to have a way of looking at them. And of course, they come in all kinds of sizes, from millimeter down to the nanometer range. And really, to visualize these particles, we use a variety of different microscopies. So this slide just shows you some of the size scales that we're dealing with here, everything from naked eye visible particulate down to maybe 1/10 of a millimeter, through the range that is accessible by light microscopy to electron microscopy, both scanning electron microscopy and transmission electron microscopy. But again, the idea here is once you've concentrated these small particles, can you get your analytical probe down to the same size so that you can really take advantage of the analysis volume to get a bit better analysis of these small bits of material. Once you have your particulate isolated in a form you can observe with a microscope, you can then isolate it for further analytical work by using microtools. So we've developed a variety of microtools at McCrone Associates that it allows us to manipulate these small pieces of material or small particles. And this is just an example of a few flakes of material being observed on a filter. And in this case, it could be isolated for techniques like vibrational spectroscopy using Raman, or for compositional analysis using transmission electron microscopy. That's a fundamental tenet of particle analysis. Observe the isolate the particles, observe the particles, and then analyze the particles. One of the most common methods we use to analyze particles is scanning electron microscopy, SEM, with energy dispersive spectroscopy, or EDS. The advantage of this technique is that it provides two pieces of information. Use an electron beam to scan across the sample and you produce two different types of signals. You produce electrons, which you can use to image the material. So the image on the left shows this fly ash sample that has been collected on a filter and then imaged using scanning electron microscopy. As that electron beam you're hitting the sample with interacts with the atoms present in the material, it generates X-rays. You use a spectrometer to measure the energy of these X-rays, and you can present them as a plot, as is shown on the right. The peaks correspond to the different elements present. So again, going back to the left, you can see right in the center of the screen a bright particle with the red dot on it. That's where the spectrum on the right was collected from. You can see it's typical of a fly ash material with aluminosilicate with calcium. The interesting feature on this particular particle is the amount of barium in it, which is actually the cause of why it appears brighter in the left-hand image. Barium is a more efficient scatterer of the electron beam, so it appears brighter. So this is one of the key techniques we'll talk about in the rest of our presentation to determine both the size and shape of the particles and also the chemical composition. So now we're going to present two examples of how we might use a particle approach. The first example was a tablet that arrived with a brown stain. So you can see on the left, here's the tablet mounted just as we received it. It's mounted on an aluminum disc with a conductive carbon adhesive. And again, this is for scanning electron microscopy. The image on the right shows the electron micrograph of this material. So you can see the stain doesn't show up too well against the background of the tablet, but if you look closely, you can see the stain is composed of particulate matter. So if you go to the next slide, here's what the stain looks like at a higher magnification. You can see there's, on the left in the electron image, it consists of particulate of a variety of different forms, both in terms of size, shape, and in brightness. And brightness, again, is a key to the composition of the material. If you do an overall analysis of the field of view shown on the left with X-ray spectroscopy, you obtain the spectrum shown on the right. And you can see that immediately what stands out is there's a large iron peak. And that's probably an indication of why the stain is discolored. It's brown. Most iron materials, iron compounds are brown. But really, this isn't the particle approach. We're analyzing this whole stain. And so the other components, we don't know the relationship. Are some of these elements associated with other elements? Which elements are coming from the tablet itself? Because we haven't done anything to isolate it, really this is more of a bulk type analysis. If we go to the next slide, we can see the particle approach to this problem. Here we've removed the particulate, put it on a low atomic number substrate, so we don't have the contribution from the tablet itself. And then we've gone in and analyzed individual particles of this stain. And now we can get a much better breakdown of the materials causing this. Again, we see that many of the particles, if we look at the data plot on the right, we see that many of the particles are elevated in iron content, as we learned from the overall scan. But we also start to see that there's particles that contain iron associated with sulfur and chlorine, which are typical elements in corrosive environments. And then there's other ones that are particles that have iron associated with silicate materials. So really we can start to break down the individual components of the stain and feed this information back to our client to help him or her determine possible sources of this material. So again, by going to a particle approach, we get a lot more information about the nature of the material of interest and hopefully then about the possible sources of this material. The second example that we're going to present, a client was producing a drug product using a raw material. The raw material is typically dissolved in solution, and when that step occurred during the production, the client observed some large brownish flakes of material in the solution. So they asked us to investigate the foreign particulate matter present in the powder sample. So the powder sample was dissolved and filtered, and the particulate was collected on a filter. Go to the next slide. And in this case, we chose an automated analysis technique. The advantage of automated analysis is you don't have to select a small subset of the particulate matter to investigate. You can analyze thousands to millions of particles. So this animation shows how an automated analysis is performed. The electron image in the center is generated in the SEM, and the electron beam then is scanned across this image, and particulate is recognized as being brighter than the background. When a particle is found, the electron beam is then rastered over that particle to determine its size and shape. So when the data being presented on the left, you can see the size and shape of the particles. The electron beam is then placed on the particle for just half a second. An X-ray spectrum is collected. The elements are determined, and then it's classified based on a series of rules we develop. And you can see a variety of fields of view then are done on one particular stub. You get a listing of all the particulate you've analyzed, and you can then start to classify them into various materials. So you can example in this example, you can see silicates, spherical particles, calcium-rich materials. You get a complete breakdown of material. So if we go to the next slide. So here's the results from this particular analysis. Using automated analysis, we analyzed approximately 32,000 particles that were collected on the filter from dissolving the raw material. What we found is a very small number of these particles, about 3 in 10,000, were relatively large, greater than 10 micrometer, copper particles. So these are the particles that the client was able to visually see in the solution once the material was dissolved. But it turns out they are a very tiny fraction of the overall particulate matter in this material. You can see that there are large amounts of typical processing residues from industrial production equipment, stainless steels, tungsten, silicon, Teflon-like fluorocarbons. And so really the large visible particulate was a very minor component of the material in this raw material. We gave this information back to the client, and they were able then to go back to their supplier and work on reducing not only the visible particulate matter, but also some of the other materials present in the raw material. So I hope we've given you a feel for how you would use a particle approach and some of the advantages versus bulk analysis. From the two examples we gave you, I think you get a feel for some of the applications, looking at raw materials or looking at contamination. There's also all kinds of applications in environmental studies, wear debris, and any other areas where you want to analyze either a small number of particles that you can isolate from a solution or a whole population of particles. So Craig, did you want to add anything else?
Just say if they have additional questions, our email addresses are up on the screen, so I'd be happy to entertain any questions that they have that are more direct nature, but otherwise we're going to open it to a general question session now.
Yes, as Kent and Craig mentioned, thanks again for attending today's webinar. And if you can go ahead and type your questions into the question box there, and we'll entertain some of them as they come in. It looks like we have a few already. If I have an unknown particle contamination or particulate contamination, what techniques other than FTIR can I use to identify the anion?
Well, again, if we had a totally unknown sample of particulate, we'd isolate it, and then we would look at both the elemental composition using SEM-EDS as we described here, and then if it turned out that it did appear that there was organic material present, you could use either IR or Raman spectroscopy. But really, it depends. I think of it as a stepwise approach. It depends on what you find in your first analysis on what the additional techniques might be. So for anions, again, it depends on If they are things like chloride or fluoride anions, techniques like SEM-EDS will pick those up very readily. If they are carbonate or other organic type materials or inorganic carbon materials, it may require Raman spectroscopy, for example.
That's right. We really do use SEM-EDS pretty much in conjunction with the IR. You mentioned what anions. Well, actually, you wouldn't be sure if it's a total unknown. You don't know that they're really behaving in an anion capacity versus the cation capacity. So we want to understand what the components of the unknowns are. And so we'll use elemental techniques to determine what the elements are. We'll use spectroscopy methods to understand the organic molecules that are present. And then once we understand those two portions of the problem, then we'll apply other methods like X-ray diffraction, electron diffraction, Raman, or maybe we want to take it in a different direction, look at a more superficial thing and use ESCA to look at the valence state of the material. So that was sort of a loaded question in the sense that you thought there was something that was an anion, but we don't know anything until we actually start to do the tests. So we pair the elemental and the organic analysis together first to find out how to get down to the next path.
Okay, James is asking, what equipment was used for the automated particle study showing elemental data and images?
So that's SEM-EDS, and the particular piece of equipment is a specialized microscope for doing automated analysis sold by FEI. It was formerly known as Aspects, and now it's an FEI product, and it's optimized for doing automated particle analysis. Most software vendors of EDS systems also have automation packages you can buy as add-ons or supplemental packages. I know Oxford, EDAX, and Thermo all have automated analysis software packages.
Okay, that kind of answers our next question from Lynn. Is automatic SEM-EDS a software function?
Yes and no. So as I said, most hardware vendors sell it as a software option. However, the example I showed in the presentation today is a system that's actually designed from the ground up for optimized particle analysis. So it can run typically 3 to 5 times faster than most of the software add-on packages that are available. So the answer is yes, it's an add-on package if you really have a high volume of samples or need a very large throughput of particulate analysis. You may want to look at a more dedicated system.
And in addition to FEI, Tescan and Zeiss also manufacture dedicated systems for those uses.
Okay, and we have a question from Sean. What method do you use to ignore bad EDS results, essentially? How do you ID what's the true data? How do you know what's there?
Bad data. Well, one of the things that we do to make sure that we produce as little bad data as possible is we'll mount our particles on substrates for which the background isn't going to be a problem. So if we're looking at metals, we can mount them simply on carbon planchettes, and we can discount the inclusion of or incorporation of the carbon. And if we are interested in looking at organic materials, then we'll have those mounted on beryllium planchettes so that there is no carbon background from the substrate. So we isolate the particle from its substrate, and then the analysis elements can be sorted.
Okay. Can you speak to how you might use Raman versus FTIR spectroscopy in evaluating organic particles that may or may not have inorganic groups too?
Well, in general, Raman, I believe, provides you more information about the inorganic groups than IR. But the other consideration is the stability of your material under the lasers typically used for Raman versus IR. The wavelength difference produces a whole different resolution between the two techniques. So Raman, you can go down to micrometer sizes, whereas IR, you're at maybe 20 micrometers. So it's more than just what type of analytical information it's providing. Is it even possible to analyze some of these particles with one versus the other?
Okay. James is asking a question here that relates to our upcoming webinar next month. And I'll put the slide up there right now. He's asking, how do the benchtop SEM type systems like the Neoscope compare to the large systems for particle investigation? And without giving away your entire talk, Craig, can you comment briefly on that?
Yes, I think that they actually compare very well, but there are a couple key issues that you'd want to consider to be the most important for your selection of which system meets your needs best. But all in all, it's a pretty close call.
Okay, and we'll learn more about that on December 17th when you and Alan address that directly in the next webinar. Let's see here. Can you explain the filtration step a little bit more? I don't understand how you can concentrate your particles if you don't know what they are and what solvents they will respond to.
Well, that's an excellent point. So a lot of times your filtration, the sample that's coming in is already in a liquid, and the client is interested in insoluble material in that liquid to begin with. Other samples will come in as solids, and the question is, can you dissolve the matrix material in a liquid and keep the foreign particulate without dissolving it? So you may have to try a couple different liquids to determine whether the foreign material is soluble in one versus another. So it really depends on the nature of the samples and the client request, but it can take some investigation. I think this is the point Craig was making. These aren't standard methods a lot of times. It's something that you have to develop for each individual request.
And then depending on the type of contamination, in some cases it wouldn't be done by filtration. In fact, we have a number of staff cleanroom microscopists who are very adept at manually isolating the particles from the matrix using custom tungsten tools. So in some cases, we might have to resort to that as opposed to a dissolution and filtration method.
Okay, and Roy is asking, do you know of an adhesive that is not carbon-based to secure the particles for EDS?
You can use indium metal. You can press particles into indium metal, or maybe some other soft metals, depending on how hard your particles are. But of course, indium is going to have a very high atomic number versus carbon, so it's going to be pretty challenging to do EDS directly on it. I don't really know of any non-carbon-based adhesives besides that.
I don't either.
Okay, and from Fiona, do you perform your SEM EDS for particle analysis under low vacuum conditions? And then she has a second part. Do you calibrate to compensate for the carbon contribution from the conductive carbon tape?
All right, the first question is about low vacuum conditions. Most of the time, these small particles won't have significant charging. If you're talking about micrometer-sized particles, there's not enough charging to worry about. If they're larger than that, or if they're particularly non-conductive, you may have to either run them in low vacuum mode or carbon coat them, especially if you want to do really high resolution imaging. The second part of the question was,
Do you calibrate to compensate for carbon contribution from the conductive carbon tape?
yeah, that's a really, really difficult measurement, especially on particles, how you get an accurate contribution of carbon from the tape. So as particles get smaller and smaller, it's more and more difficult to combine the interaction volume to the particles themselves. So overall, the answer is no, there's not really a robust method for doing that. I think the better solution is what Craig mentioned, put them on a substrate that doesn't have carbon in it to begin with, either boron or beryllium.
Okay, looks like our last question here. What kind of filter is recommended for particle analysis?
So the filters we use are membrane filters, so they have a flat, smooth surface. These are ideal for doing imaging directly on the filter, as we showed in the SEM, and also for manipulating particles with microtools directly on it. So membrane filters can be purchased in a variety of different materials, polyester, polycarbonate, and also fluorocarbon materials. But those are the ones we recommend.
Okay, great. Well, that rounds out our questions, and I'd like to thank Kent and Craig today for their information, and everybody else out there who attended. And be sure to join us for our next webinar on December 17th when our presenters, again, Dr. Craig Schwant will be with us, and Alan Vitus of Macrone Microscopes and Accessories will compare the JEOL Neoscope to a full-sized scanning electron microscope. Thank you.